I posted in Google Classroom last night. Some of you after school were able to hear it in person. As soon as class ended, I got over here to the notes and I was like, what the crap just happened? Because it was fine. It was like, okay, a constant velocity, find the area. It was fine. Okay, it wasn't a constant velocity, but it was linear, find the area. And then all of a sudden it was not so fine. But I was still like, okay, I mean, I guess I could have last year introduced the whole idea of how to write Riemann sums, but it's kind of weird that it's in section 6.1, but okay, yeah, Riemann sums, all right, fine, Riemann sums, we stop at n, we're not going to infinity, okay. And then I was like, what? And I was like, okay, we can approximate volume with geometry. Anyway, I totally kind of like BS'd what was going on towards the end of notes because I was so confused as to why we had all of a sudden like integrals and why we had properties of definite integrals when our title of section 6.1 was just estimating with Riemann sums, non-trapezoids. So I was like, where's the left? Where's the right? Where's the midpoint example? And it wasn't there. Long story short, if you guys look at right here, I had to rename the notes that we were taking yesterday. Can anybody see it? Are you close enough? What's it say? All mixed up. Why? Because literally I started scrolling through my notes and I'm like, it's all out of order and I'm missing like 2 sections entirely. I don't know what happened to my notes from last year. But the nice thing is, what else is there besides the all mixed up one? The one that I have open, which is not all mixed up. So, guess what? I'm going to delete this page for now. Even though it was a good page, good information, it's gone because it has nothing to do with 6.1. I'm deleting that for now because that actually comes in like 4 sections later when we're reviewing average value formulas. I'm deleting this one because properties of definite integrals are good and all, but this was actually supposed to be a back of your homework spiral challenge problem for you and your group after we talk about everything to do with definite integrals. Well, and let's just talk about the basics of 6.1, including a Riemann sum approximation problem like n equals 5 and how do you do it? Now some of you are like, I was fine, I did homework, I remember everything to do with Riemann sums by myself. Good! I'll post for you section 6.2 homework, you can play with that. For the rest of us, we're actually going to get a Riemann sum example for the Riemann sum homework. Sound good? Awesome. But first, before we do that, play around with this example as I post for you section 6.2 homework, which is definitely not due tomorrow. It will be due Thursday instead. But you can start playing with it if you're like, I'm a master of Riemann sums. I don't need your petty examples. Okay, that's fine. I don't mind. Some of you are. Some of you are. But for the rest of us, no, we would at least like to review what homework was supposed to be on. Sound good? Okay. But as I do that, I will go take last year's homework assignment, which has pictures of them at the Great California Shakeout just chilling, and change it to be what you guys want to see. I think I posted this because I was showing them so they could be working on it during the Great California Shakeout drill. So I have like pictures of the book, but you guys don't need it. Because you have your book, you're not sitting out on the field trying to get stuff done. Thursday the 24th and 8 a.m. We'll see. Guys, I'm really trying not to lose an entire day. I don't think this will take us an entire day. It was a really short section. So I'm going to try to finish 6.1 and start 6.2 like we're supposed to today. Okay? But the homework is officially up if you guys want to move ahead to section 6.2. I think it's just moving into antiderivatives, if I'm not mistaken. Definite integrals and antiderivatives. All right, for the rest of us, let's do the examples we were actually supposed to do. Sound good?
Hi. Hi.
What are you guys up to?
The whole English class with their books.
Okay, a beach is eroding. There's eroding. This totally sounds like an FRQ question. Actually, it was one here. Not this easy. Not this easy. A beach is eroding at a rate of 3 cubic yards per day. How much of the beach will be lost over a year? It's a simple distance equals rate times time, but I also want you guys to see it's a simple constant velocity. And so that constant velocity of y equals 3, where y is my velocity function, right? Or my rate function. How long am I having this go for? of you guys hadn't really connected the whole area idea to this equation before. Do all of my units work out? Because the days are just going to reduce. And I end up with, that's a 5, and that's a 1, and that's a 9, and that's a 1, and that's a 1,095 cubic yards. In context of the problem, what about those 1,095 cubic yards? Is how much the beach, wait, how much the beach lost? What is it talking about? Sand. What about the sand?
Cubic yards of sand being lost.
How is it being lost?
She's eroding.
Eroding meaning being washed away, and so there's less of the beach that remains, right? Does that make sense? Guys, literally, this problem is in this book, this AP edition of a book, because it literally was on beach erosion was an FRQ problem one year. Anyway, a lot of kids didn't know like what was going on with the beach and the erosion, and it didn't actually use the word erosion, which was kind of mean. It actually instead just used like losing sand. It was kind of confusing. Anyway, let's get to a Riemann sum example. That's the point of section 6.1. So how do you find area under the curve? Well, we're not answering that question today. We're finding how do you estimate. That's what section 6.1 homework is on, which is why we're not grading it until tomorrow, because some of you got to homework and you're like, huh? Because we didn't do an example. So our illustration is a particle. Context. A particle starting at x equals 0, moving along the x-axis with a velocity of v equals, not a line and not a constant, it's a curve. Velocity is curved, t squared, for t greater than or equal to 0. Where is the particle at 3? Where is it at? Ooh, well, where did it start? It started, initially, it was at 0 plus, you guys remember how we have to do the initial position plus the change? And how is the change found? Area. How much sand eroded? It's the area, it's the rectangle. How much did the particle move? It's the area, it's the rectangle. It's just the change that occurred in the position. So, somebody already said, Lainey, was it you? The initial position is just 0, so I get to go ahead and say, oh, sweet, it starts at 0 and changes how much, and where does it end up? This one's easy. If the AP wanted to make it hard, or at least trick some people into getting it wrong, what would they have done instead?
They would have an initial.
Yeah, they would actually have x starting at something like -5 or 2 or 7, right? Anything other than 0, they could have definitely caught kids on, because kids would have forgotten to add that initial position plus the area. Okay, so what's the point that we're doing right now? How do we do area under a curve? Oh, it's a definite integral from 0 to, no, with Riemann sums. Oh. Alright, kiddos. So we're going between 0 and 3, right? Which they have it marked out. If I was to estimate the area using these subintervals, can you guys tell how many subintervals they've marked out?
1, 4.
In between 2 and 3 is 4. So therefore I have 4, and I have 8, and I have 12. And as I had to remind one of your classmates yesterday, remember, if they say to estimate, which I know, in the words that you see, it does not say estimate, but in the homework for 6.1, that was what you were supposed to be practicing, the skill of estimation using rectangles. If they use estimate, is the exact definite integral answer going to be right? So you have to find out the correct estimation. So the correct estimation. What kind of Riemann sum do you guys see them illustrating over there? A midpoint. Does it actually say which one we're supposed to use here? Nope. And why? Because I want us to review all 3. So, in your homework, real quick, here's what you're going to see. You're going to see LRAM. You might see RRAM. And you might see this guy, MRAM. Anybody figure out last night what those stand for? Left, right, middle. Riemann approximation. I don't actually know what the N stands for, so left, Riemann,
right, middle. Riemann sum.
I don't know. Funky shirt, we'll just go there. So LRAM, RRAM, MRAM, basically left, right, midpoint. Remember, every time you're doing this, the easiest way to figure out your intervals is to figure out who's A, who's B, beginning and end. And how does it work if I am splitting up into 12ths?
Method? It's method. Ooh.
Oh, method. Oh, that makes sense. Nicely done.
So like right.
So I have 3 minus 0 all over 12. Guys, what am I going by?
Rectangular approximation.
1/4.
0.25.
I like Riemann better, but okay,
Wait,
rectangular.
Wait.
I'm going by 0.25s, right? Okay, so if I'm going by 0.25s, there's going to be 1, there's going to be 2, and then we're going by 0.25, so half and then fourths, and then half and then fourths, and then half and then fourths. Got it. So therefore, if I'm doing an LRAM, well, can I actually just, can we just make a whole separate paper, because this is going to get messy real fast. And then can we talk about how to use a summation, how to use sigma notation to summarize a very nasty, why is this nasty? Do you remember what I'm going to have to do? Whether I do it the long way or the short way, what do I still have to do? Yeah, I have to add up all, oh my goodness, you gotta be kidding. I'm not kidding, why? How many did it say?
12.
So wait, we like math because we're lazy. We want to learn a method and be able to use it and not have to memorize tons and tons of stuff or write tons and tons of papers, right? So this doesn't look short and sweet and simple, so let's find patterns. What's one pattern that can shorten this entirely excessive addition? Oh, the base is the same? Why? All the bases are going to be going by 1/4, right?
Yeah.
Oh. So every single one of these is going to have the exact same base of 1/4 all the way down, true? Times. What comes next? Base times height. And to do height, don't I plug into my function, which in this example is a velocity function? Don't I plug into my function?
Yeah.
Now what am I going to plug in for my LRAM? Let's just say we're doing the LRAM right now. Starting from the left, which means
0.
starting from A, which is 0. So I'd have V of 0, and then question, where would I end?
2.7.
Right before 3, and so 1/4 right before 3 would be 2.75, right? And if you count up all of those from 0 to 2.75, counting by 1/4, you would have 12. If you went all the way to 3, you'd have 13. That's incorrect. Now, what's going to be different if I had an RRAM instead? So you have still a base of 1/4, right? But it'd be V of 0.25, and you would go all the way up until V of 3. What would change if you had an MRAM? In the middle. So you wouldn't start at 0 or 0.25. You would start at 0.125. And you wouldn't end at 2.75 or 3. You'd end at 2.875?
Yeah, that's right.
We go halfway in between, so we need to add 0.125, and so adding 0.125 is 0.890. 890? No, that's not right. 875. Yeah? Anyway, you end at 2.875. Now pause. Hold on. We just said that we were lazy mathematical people, at least somewhat. So wouldn't it be nice if we could summarize this into a sigma? And then use our calculator to do it for us? Now, last year, I totally would have had you guys put the velocity function into your y1. And I would have said, sweet, 1/4. Oh wait, couldn't we bring the 1/4 outside of everybody? Because all of them have 1/4. And so I would have had you bring 1/4 outside of everybody. But even after doing that, if you were using your calculator, I think I quickly showed you the Riemann sum idea. But if you didn't understand the Riemann sum idea, you would still have to do 1/4 times V of 0 plus V of 0.25 plus V of, oh dang, how many of those am I going to have to do? 12. Oh. So you do y1 of, y1 of, y1 of. If you realize it's just t squared, I guess you just do 0 squared, 0.25 squared, 0.5 squared, 0.75 squared, but still it's tedious, right? what's that really cool Greek letter that signifies? Taking a long extended addition and summarizing it, a sigma. And how does it work? Ready? How does it work? It's helpful for a few things that are coming in the future, so here we go. LRAM. We knew that we're going for 12 different rectangles, true? So one way of showing that is from 1 to 12. So plugging in 1 should be my first rectangle, 2 should be my second rectangle, 3 should be my third rectangle. But what needs to happen? What needs to happen? Well, the 1/4 is good for everybody, so he doesn't have to change. For the first rectangle, 1/4 is my base. Second rectangle, 1/4 is my base. Third rectangle, 1/4 is my base. For every single height, I'm going to be plugging into. Wait, why is there a square? Whoa, whoa, whoa. What am I doing? Because t squared is the guy I'm plugging it into, right? So here's my base, here's my function, but don't I need, every time I plug in another number, don't I need it to transition one place farther on my number line and plug in? So hold on, how do I do that? What am I going by? 0.25s. Oh, so why not just do 0.25 times n? I have 1.25, 2.25s, 3.25s. Oh, 1, 2, 3.
Doesn't it count for the ones?
Why do I have to group that and say, yeah, that's great for RRAM? Why isn't that LRAM? Where would this start? What rectangle would it start at? F of 0.25. It'd start one away. That's the right Riemann sum approximation. That does 0.25 all the way to, check it, plug in 12. 12 times a fourth is 3. This would go from 0.25 to 3. That's the right one. Okay, so hold on. What would I have to change for the left one?
Minus so you put the n.
I need to come back one, and where's my place? Here. I need to come back one, right? So can't I just plug in 1/4 times 0.25 times n minus 1 squared? That would move it back one, right? Plugging in 1 minus 1 is 0. Ooh, good, it's starting at 0. And then 3, well, that would start back 1 of the 0.25. It would go to 2.75. Perfect. Now, how would I make the n ring? We talked about a second ago. We have to land smack dab in the middle. So how do we land smack dab in the middle? Not one to the left, not one to the right, but in the middle of the 0.25s.
You do the same thing as the LRAM, but it's n minus 0.5.
N minus 0.5. So instead of going all the way back, you only go back halfway?
Yeah.
That's an interesting way of thinking about it. I think I would have done, just off the top of my head, I think I would have done 0.125s, but plus, because the 0.125s is where I start, right? But I have to start one removed, and I have to jump by 0.25s after that. So I would have thought about it very geometrically, I suppose, like thinking of my actual number line and where I'm landing. Ladies works, everybody. It's just not the way that I would have thought about it, so I'm just showing you. So that means that's not the way that some of you would have thought about it too. I'd be like, okay, I need to be at 0.125, but I need it to jump by 0.25s every time. And I need that to happen every n, so that needs to jump by that, but I need it to start at 0. That's how I would have done it. Because I'm still jumping by 1/4, but I have to start a little bit removed from 0. So technically, this one was starting at 0 plus, this one's starting at 0 plus, this one's starting at 0.125 plus. But then, Lainey, how did you say to do it? You said same thing as the LRAM.
But it's n minus 0.5 instead of n minus 1.
have 1 whole 0.25. Oh, just kidding, half of that. You'd have 2 whole 0.25s. Oh, just kidding, 1 and a half of that. 3 whole. Oh, just kidding, 2 and a half of that. Yeah, you would end up landing in those halves, which is what you need. Oh, but check it. Isn't this going to end up being the exact same thing? I have 0.25n, 0.25n, minus 0.25 plus 0.125 is minus 0.125, and that's minus 0.125. So ironically, it's the exact same thing, just thinking about it 2 very different ways. Anyway, sigma notation. Ooh, it's a party. So guys, here's a question. Ready? Can I make you into a graphing calculator, Riemann sum approximation programmer for a second? Yes. What I want you to do is, what kind of math would you need the program to do to be able to solve this for a student? You ready? Okay. Go. What can you do? What kind of math would you need the program to do to be able to? There are right, left, midpoint, Riemann sum approximation programs that can be used to approximate. Hint, hint, hint. Approximation is all we can do if an antiderivative is impossible. Some antiderivatives are impossible.
Yeah.
How would you program a computer to do this, which would be a pretty stinking close approximation? N equals 100. Go! P.S. Use a sigma. Please use a sigma. Do not write a sub 1 to a sub 100. Bad idea. You don't have to do the computer programming language, just what math would you need the program to do?
I would assign like different variables. Like I'll say x equals y is n, x equals a. I'll just do that. I think that would work. That is a great one. I'm gonna try something. What's your law?
I gave you everything you needed, just it wasn't all written out in the problem we just did. If you want, the easiest one to do is the RRAM. You could start there. We actually wrote down notes yesterday about the LRAM and the RRAM. Maybe you guys could be using those notes. They were kind of nice. We wrote down notes yesterday about how to set up an RRAM and an LRAM. Maybe that could be helpful.
I think it does start at 5. What do you think, Chinna?
Giving you time. I don't just want to give it away. Any program is only as good as how general it could be made.
Yeah, it took.
You can make it work for one and not for everything. Well, it's not such a great program.
Yeah, same.
If you formed the RRAM, how would you form the LRAM? How would you form the MRAM? And then think, wait, is there a pattern? Is there a formula to this?
3/100x
What would it stand in there?
I don't remember.
I don't know where it would start. Like the
Start
start.
five.
I don't know where it would start. What is the bottom part of the
Oh, okay,
solution?
that's for all
It's
round.
all-
For LRAM, instead of just
Is that like increments?
Yeah, I think so. Eventually it adds up to
And then
or it goes up to
minus 0.5.
so it should still be
Middle
Okay.
round, what would it be?
Okay.
5.5. Oh yeah, you're right. Yeah, the beta for that. I don't know if that's that.
You got it?
Yeah.
So then think, how could you generalize it for any A, any B, any N, and any F? And some of you just looked in your notes and you're like, okay, well, let's see if you understand it. But for those of you that haven't looked in your notes and you're trying to develop it yourself, how could you generalize it for any A, any B, any N, and any F? Now the cool thing is, if you guys can figure this out, couldn't you technically never need to check a back of a book or a CalcChat or a Slater for a Riemann sum again? Couldn't you just check it yourself on a calculator? Now, the AP doesn't really let you use calculators on Riemann sums, and they do things like non-equal subintervals, irregular subintervals. That's a bummer. They make it so you couldn't just use a program, but for any time you're doing a Riemann sum with equal subintervals, if you can figure out how to generalize it in a Riemann, like in an actual sigma, man, life could be nice.
Floating.
yeah, same.
What you got?
Oh shoot.
Oh no, I
Where
didn't
am I?
know that first. I had the
What was your base?
3/100. Oh no, cancel. 3/100. It's just that.
Oh, you mean you did B minus A all over N?
Yeah.
Oh.
Is it something different?
So, 8 minus 5 is 3, and 3 over 100.
Hey, I got it. Yeah.
And then,
What if I square?
did you plug into F something? Right?
Yeah.
For your heights? How did you progress from one S to another? What did you put for RRAM?
Times
3 over 100 times,
X.
in
N,
context
sorry.
of mine,
N.
yeah, wherever you put. N.
The threes out. There's like another 3 outside of that. Because it's 3. Because the equation is 3 x squared.
Oh, got it. You mean my S
Hold on,
axis.
I got
Got it.
Yeah.
There you go.
I'll do the height.
And then,
I think I clicked the wrong.
That's
I got
So
it.
right now, this would start at 300ths, and then it would go to 600ths, and then it would go to 900ths. It's wrong. Why do you have to have a 5 plus?
Oh shoot.
See it? You have to start from A. So technically, we had to start from now. The last problem we were starting from 0, so you didn't see it. I said it, but you might not have caught it. But this one, I have to start from, whoever your A is, and then you have to do your B. Well, wait, hold on. Isn't this just your delta x, technically? Right? Your B minus A all over n, that's your delta x. And then we're doing our delta x, which is our 3 over 100, times n. Oh. Is that just always the R-RAM formula? Which is why yesterday, even though it was a bit premature, and I kind of just busted it out of nowhere. Oh, I deleted the slide. Ah! It's a bummer, man. That's okay. Good thing it's in our PDF. Did you guys find it in your notes, or did you guys just go like crossing out stuff when I said ignore it? What did I write yesterday? Hey, delta x times f of a plus delta x. Now, I said i's because I was talking about my little index, but I changed it up a little bit today. But could this be a helpful summarization for how to do left and how to do right? Wait, the left is different. Yeah, because we have to start back one place, right? And what would we do if we had to generalize from midpoint? We have left, we have right. My curiosity is, well, what do we do if we're generalizing from midpoint? I'm bringing this back into the notes just because I decided I actually did want it, because we were talking about how to program Riemann sums. Midpoint, what would change in a general sense?
Instead of I minus 1, I minus 1.
Or can divide something by 2. Like the base by 2.
Those are the two different ways, yeah. One way is Lainey's way and one way is my way, I think, from what I'm hearing from Patricia and from Kevin. Because for MRAM, I'll do black. Oops, I can't spell MRAM. Awkward. Midpoint rectangular approximation method. We would still have our 100, right? We would still have our 300s, right? And we would still have our 3 times somebody squared plus 1. Okay, I heard Patricia saying start from, we still have to do 5 plus, yeah? Kevin was saying cut something in half, and Patricia was saying start from a different direction. So who has a way of actually putting it in?
3 100s over 2.
3 100ths over 2, so we could do like 1 half. 300ths, which would get us in the middle, but wait, hold on, it won't get us to the middle quite yet. What do we have to do?
Times n minus 1.
Oh, now we're mixing the two, and we're gonna get it mixed up.
Just do n minus 1.
Times n minus 1.
If you're doing it that way. You square the thing.
So wait a minute, hold on. This one says keep adding 600ths. But the problem is we have to add 600ths and then jump 300ths, and then add 600ths and then jump 300ths, and then add 600ths and then jump. We have to make a full jump in between. So we have to go from halfway to halfway, which means a whole unit away. So hold on, that's not going to work so good. That's going to get us way too many.
Remove the 1 half. And then
Remove the 1 half.
You put the 1 half somewhere else. I was trying to find
N
where.
minus 1.
Maybe 5 over 2.
This was Lainey's way. Would that work? Because 1 minus a half gets you halfway in between. 2 minus a half gets you 3 halves. 3 minus a half gives you 5 halves. That will land you halfway. So that's the easiest way. Is just instead of doing n minus 1 to go all the way back to 0, n minus a half, because then you're jumping every whole number, take away a half, every whole number, take away a half. Your way, Kevin, would have been
5 over 2.
3 over 100 times 1 half being taken away from 3 over 100 times n. Like that's ultimately what you would have needed to think about in that. You can go 3 over 100 times n like the right, but every time you have to subtract a half of that to go backwards. So your 3 over 100 go back, 3 over 100 go back. So how could we generalize from the midpoint? I think Lainey's way is probably the easiest, yeah? So I can go from my I equals 1 to n f of a plus b minus a all over n times I minus a half. Because this isn't you necessarily taking a half of the subintervals. This is you taking a location, whatever that location is, by your delta x, and then going back halfway in that unit, whatever it is, 1/4, 300ths, whatever it might be, times. Now, how could this notation be made a little bit simpler? If you replace all of your b minus a over n's with delta x's. That would have just made it a little bit prettier. Because then you would have f of a plus delta x times I minus 1, or I minus 1 delta x times delta x. And that's where some of that limit definition of a Riemann sum comes into play. Whew. Anyway, do I think you have any n equal 100s in your homework? No. But if you have any n equals, you technically, in keeping with what's actually going on, have a way to program and solve it quite simply, quite easily. Just be careful. You know, the AP is going to put a huge wrench in this entire, I can use my calculator to do it for me, because they say, well, we're not going to make them equal. Aww, party poopers. And then we have to adjust if it's not equal. Kiddos, I think with that, we technically do have like an exploration, but that would have pretty much gotten you into programming. I'm going to take that away. And then you had this one, which was another example, but now that that was so close to what I just did. So let's not stress about it, cool? All right, that's the end of section 6.1, homework number 19. Oh, that's fun, due tomorrow. I'm going to leave this guy off because that would have been our opener problem if we had had time. And let's just go to section 6.2, which remember, we needed to start today because that was our goal. If I hadn't had a mixed up set of notes yesterday. So apologies. We're back on the same page, and some of you learned how to use that sigma summations a bit better than you've ever done before. Yeah.
What does the bottom of the summation, like the I, what does it stand for?
Index, I think, is technically the word for it. The index of the summation.
What if it wasn't
But it literally just means or represents the variable that's going to be used inside the argument of the sigma. And progresses through all the integers from the lower to upper bound.
What if it was like I equals 2 or something?
Then you just start at 2. Does that make sense? So the I itself is just the variable, but the number down there represents the first integer that you plug in, and then the top one is the last one that you plug in. So you could go from like 5 to 100 or 10 to 17. You don't have to go from 0, just 0 to 1 is usually where we start. So wait a minute, hold on, this notation should make total sense because what are they doing? They're multiplying bases times heights, right guys? F of C, well, F of C sub K, what on earth? Why is there a C and a K and a, I get the K, okay, whatever. We were using n's, but I get it. They want to use n for the number of rectangles. Okay. So if n is the number of rectangles, this can't be n. They probably don't like I because it's usually imaginary numbers in like the broader scope of math. So they use something else like K. But why is there a C? So F of C sub 1, C sub 2, C sub 3, C sub 4, delta x. We could technically put a little K down there too. Because sometimes the delta x changes. But who is C?
Would there be any chance like the K is not equal to 1?
Not for Riemann sums, but in the broader scope of summations, yeah. But not for Riemann sums, because Riemann sums we're starting from the first rectangle and ending at the last. So this stands for start at the first and end at the last. So yeah, in context of Riemann sums, it should just be 1. Not that you can't write it a different way, but that's proper notation. Guys, C is, chosen arbitrarily in the case. Chosen arbitrarily? No. This was really important a second ago. It was from the left, or it was from the right, or it was from the middle. But wait, what are we doing now with all of these Riemann sums? We're having the number of rectangles go to infinity. So guys, if we're approximating from the left, or from the right, or from the middle, if we're adding in more and more and more it doesn't matter, then what was the easiest one? If you had to actually set up a definition of a Riemann sum, the easiest one to use would be RRAM because it has the least amount going on. All I have to do is just A plus delta x times k. The easiest one to use would be RRAM, but the point is that it doesn't matter what you're using inside each subinterval. It truly is arbitrary because whatever you're using, as the number of rectangles increase, they are all the Riemann sums are going to approach the exact answer. But the RRAM, the right approximation, is the easiest one to state, so he's the one that's normally used in the limit definitions. I was going to show you if they had unequal subintervals. If they're not equal, you couldn't just say that delta x is one thing and one thing only, but only one little thing would change. You would have the limit as n goes to infinity of your sigma k equals 1 to n. Sometimes they also use the i's. I mean, that's a thing. Just this notation, this book didn't like it. They could have done f of c sub I or c sub k times. All that would change is delta x would also have a k because this could change every time. 1 second it could be like a length of 1, a length of 3, a length of 1/2, like the AP does in tables. So if unequal, only one little thing changes, that could change as well, not just the c's but also the delta x's. The Leibniz notation though is where we got that. Remember Newton and Leibniz, the two guys who were at odds? Newton liked his differential notation, dy dx for derivatives. Leibniz liked his dot notation, the f prime, f double prime, f triple prime. Leibniz was the one that brought in the integral sign, the elongated s for summa for summation. I don't know if you guys necessarily need to write down all of these terms, but I did like this even better than last year's textbook, this coverage of a definite integral. You have the integral sign itself, the lower limit, the upper limit. The entire thing is the integral of f from a to b. The function is the integrand. We talked about that a bit last year. D who? Well, D whatever the variable of integration is. And then when you solve, when you find the actual value, the exact area, you have evaluated the integral. So all of that to remind you that an integral, even though, yes, you find an antiderivative, you go from A to B, and for you guys, you do know how to integrate a lot. You're going to learn how to integrate more. But there are functions that are impossible to integrate, are non-integrable. Like non-differential, but non-integrable. Approximation techniques are not archaic. They are not useless. They are still very necessary. But as we go into second semester, we'll learn better approximation techniques for things like this. Oh, look, there's integrable. Huh, there he was. All continuous functions are integrable, able to be integrated, and some discontinuous functions as well. Some. Uh-oh. So what's coming? Ooh. So what if you're given something like this? Wait a minute, we haven't even learned antiderivatives yet. Oh, no, we did. Hold on, this book taught us antiderivatives in a weird place. Where did it teach it? Was it last chapter? Yeah, antiderivatives randomly showed up with like MVT. Anyway. You have learned antiderivatives, but let's just say you haven't learned this one yet. So why did the directions say use the graph to calculate the, okay, you just theoretically learned that this is a representation of the exact area under this, between this and this. Okay. So how do I solve? Graph, because who is this guy? It is graphable. But graphable in a way that's a geometric shape that has an area formula that I should know because the square root of r squared minus x squared. Why did I say r squared? Are we still forgetting who this is? It's a semicircle. Not a whole circle because it's only the positive square root. True? Ooh, it's a semicircle with a radius of? Death. It's just 4. Don't go believe in the chapel speaker from yesterday. I mean, do on the things that were true. But from being a servant of darkness to a servant of light, from teaching math to teaching Jesus. Oh. Well, I caught it. Anyway, you guys are too busy looking at me and snickering. Anyway. Question. What is it? Why is it 1/4? It's a quarter circle, not a half circle. 16/4 is 4 pi. Now, you're in BC. Oh no, we only have 30 seconds left. I was going to show you how to actually solve it. This is so sad. There is a way to solve this, guy.
Oh no.
I'll save it for tomorrow. It all comes back to a triangle. It all comes back to a triangle. You guys remember how we did inverse trig and I said we had to go to a triangle? That's how you solve this integral, by hand, not by geometry. Alright, cool kids, I'll see you later. 6.2, not due tomorrow. 6.1 is, see ya. Why is there a line in my thingamabob? Why is my computer frozen?